Good morning, all. So I'm going to explain a problem on heat transfer, how we can solve using FEM method, finite element method. So here is a problem given. So find the distribution in the 1D pin shown in the figure. Take two elements for FE idealization. So here this pin has to be considered as two elements. So what are the things given here? We have given the T1 because two elements. So I had to write the FEM model for this. So T1 140 degrees. So that is 413 Kelvin. Length of the whole thing is given as 5 centimeters. So since we need to consider the two elements, so L1 and L1 equally divided 2.5 centimeter. So T infinity is given as 40 degree, that is 313 Kelvin. K is given as 70, H is given 5, then radius is given as 1 centimeter. So since we need to find out the area, that is pi r square, so pi r square is 3.14. As well as we need to find out the perimeter, that is 2 pi r. So r is 1 centimeter, so perimeter we are getting it as 6.28 centimeter. Now here is the FEM model for this. So I considered that two elements, 1 and 2, and 3 nodes. So at the 3 nodes, I have defined the temperatures T1, T2, and T3. So L1 and L2 are the length. Now we need to find out the stiffness matrix for heat conduction. Conduction. So if we see the stiffness matrix for conduction is given by AK by L into 1 minus 1 minus 1, 1 where A is the length, K is thermal conductivity, L is the length of the element. So since we need to find out the heat conduction matrix for both the elements K1 and K2, so I have substituted all the values A, K, L value I have substituted. Since the length of the element is same for both and the K values are the same, so K1 and K2 we are getting it as same. And K1 and K2, or K1 for the first element, that is for the first and second node. K2 is considered for the second node, that is for the second and third node. Okay. Now you find out the global matrix for stiffness matrix for the heat conduction only. So Kc is nothing but adding up of K1 and K2. So K1 is for 1 and 2. So K2 is 2 and 3. You know how to find out the global matrix. So add up K1 and K2 for 1, 2, 3 nodes. So this is a Kc value I am going to get. That is the global stiffness matrix for heat conduction. Now we need to find out the stiffness matrix for convection. Okay, since T infinity is given for us. So KH is given by, so we have derived it in the last class, HPL by 6, 2112. So first element KH1 I considered, second element I considered KH2. So we have given this H, P also we found out perimeter, L is the length divided by 6 and this matrix. Okay, so since all the values are same, I will get K1 and K2 as same, since all HPL is same for both. Now again here also we need to find out the global matrix, global stiffness matrix for the convection, that is KH1 and KH2. I added up, so I got KH value. So this is the global stiffness matrix for convection. So earlier we got the global stiffness matrix for conduction. Now we need to consider the global stiffness matrix considering convection as well as conduction. So Kc value I have written global, Kh value I have written here. So I need to add both the values. Directly we can add it because this is also global matrix and this is also global matrix. So we are adding both the global matrix. You add up the corresponding values of Kc and Kh. So this is the final global stiffness matrix I am getting for the fin. Then we need to find out the force vector due to convection. So force vector due to convection is given by Fh is H P infinity PL by 2. So I have derived it yesterday. I have shown how we are getting it as H P infinity PL by 2 1 1. Okay. Now you substitute all the values I have given with the T infinity, T perimeter as well as length. Substitute it and get the values for the force vector due to convection for the first element as well as the second element. Again here also we are getting it as same since all the values are same. Then you find out the global force vector due to convection. So we are adding it up first and see. First, this is FH1 for the first element, that is corresponds to 1 and 2 node. FH2 is for second and third node. It is meant for second and third node. So while you are adding it up, so first element only 1228.525, and for the second node we need to add the both the matrices. Okay, sum of that. So this is the force vector we are getting for the force vector due to convection. You are getting global matrix. Now we need to write the equilibrium equation. So equilibrium equation, all of you know, it is K into T is equal to F, where K is a stiffness matrix, T is a temperature matrix, as well as F is a force vector. So I have substituted all the values over here. Now here directly we can't go for the elimination method. First let us consider the second equation, wherein I will get all the coefficient of T1, T2 and T3, that is minus 74.837 T1 plus 228.17332 minus 74.8373 is equal to 2457,050. I am considering only the second row. Okay, but we have given with the T1. T1 is given as 413 Kelvin. So you substitute here T1 and you just get the equation as 228.17332 minus 74.83733 is equal to 24,570.5 plus this value 74.837 into the temperature 430. So I am getting this equation. So just I have mentioned it as star. Now we can eliminate because we know the value of T1 because this is unknown. So in the elimination method, what we'll do is we will eliminate the row and column corresponding to the boundary condition. Here the boundary condition is T1 is known. That means I can eliminate the row and column corresponding to T1. So that means I am eliminating first row and the first column. Once I eliminate it, now here if I eliminate it, I am getting this matrix. But here, since I have changed it, T1 value I know, so you replace the second value that is 24570.50 by 55,479.42. So rest of all the coefficients, this matrix you are retaining 228.173 minus 74.837 minus 74.837 11.4.086 that you are maintaining. So keeping it as it's only this value will change since the T1 value is known, your matrix, your equation changes and this value, post vector value will be changing as because you need to replace the value by the star equation. Okay, you are replacing that equation by the star equation. Now on simplification, now we got the two equations. So you can go for the simultaneous equations. While if you solve it, we'll get T2 value as 353.938 Kelvin, T3 value as 337.797 Kelvin, and we know T1 value that is already given. So that's how we can find out the unknown values of the temperature.